Hi everyone, welcome to Spacy 3 Masterclass tutorial. This lecture is going to be almost a 3 hours long lecture, and in this we will be covering from the starting of the Spacy to the end of the Spacy. So it is kind of the end to end lecture for Spacy 3 Masterclass tutorials. We will be discussing a lot of things in these lectures, like what is the Spacy, the features of the Spacy, how you can install Spacy. Other than that, we will start discussing the linguistic annotation in the Spacy, tokenization in Spacy. Other than that, we will be also discussing other features of the Spacy, like the part of speech tagging and the dependency parsing, in which we will be also discussing the visualizing the dependency parsing by using the Spacey. Thereafter, you can use there a sentence boundary detection. That's mean there is the paragraph. You can break down that paragraph into the set of the sentences. Then there is the stop words, lemmatization, stemmings. Although the stemmings are not the part of the Spacy, but knowing the stemming is really good. We will be also doing the comparison between the stemming and the lemmatization. I'll be also showing how you can do the word frequency count in a given text data. Thereafter, you can do the rule-based matching in the Spacy. So the rule-based matching in a Spacy is actually a very useful when you are working on an unstructured data set. You want to match some particular entity, you can use their rule-based matching in Spacy. There is the entity matcher. It is kind of the rule-based matching in Spacy, where you will be matching the entity based on the rule which you define. Then finally, we will be discussing the named entity recognition, and then word to vector and the sentence similarity. That's mean a text data will be projected into a vector space, and then based on those vectors which are there in the vector space, we will be calculating the similarity between the words and the sentences. So this is going to be a really very fun lecture series for the Masterclass Spacy 3. Before we get started with this lecture series, I would like to introduce you a startup which is actually run by one of my friend. She has started her own sustainable and comfortable fashion startup. It is known as House of Dona. You can get all ethical and hand-picked clothes from the House of Dona. These cloths are made of the environment-friendly fabrics. I would like to humbly request you, please visit houseofdona.com once and share it with your friends and the family. You can visit House of Dona by simply typing here bit.ly/KGP Talkie -Dona. If you don't remember this long URL, you can simply type there bit.ly/KGP Talkie -Dona. Currently, they are offering up to 50% discounts on all their clothes, and they are also doing a free shipping across India. All right, so let's go ahead and get started with our lectures. Hi everyone, today we are gonna learn about a Spacy 3.0. This is a master class. This class would be divided into a multiple tutorial, and this one is the first tutorial where we are gonna start Spacy. So we will be coding Spacy in a Google Colab. You can open Google Colab from colab.research.google.com. This is a free tool to use. You can use GPU as well as CPU here. It has a TPU as well. Since we are starting here as Spacy, so we don't need a GPU and the TPU here. You can start with the general CPU versions of the Spacy. Although Spacy comes as a pre-installed on Google Colab, but that version is currently 2.2 version. You need to install this Spacy 3.0 on Google Colab separately. So you might be wondering that what is the Spacy? Spacy is actually a tool in natural language processing to process the text data. In Spacy 3.0, Spacy have included the transformers, classifications, and better and improved models. So basically Spacy 3.0 is much better than the Spacy 2.0. This Spacy is a free open source library for our almost half of the NLP. You can say if you are the beginners, you can say almost all your NLP requirement can be fulfilled by the Spacy itself. It has so many features which you can use during your machine learning journey. Like in NLP, you can use the tokenization, parts of speech tagging. These terms might be new for you if you are hearing these terms the first time, but do not worry about that. In coming tutorials, we will be covering separately what is tokenization, what is parts of speech, dependency parsing, lemmatization, all these things. As a beginner, if you start your journey as an NLP engineer, in coming days, you will be learning text tokenization. That's mean how you want to segment your sentence data. The parts of speech tagging, how each words are arranged in a sentence. You can give them a parts of speech tagging there to find out the dependency there. So basically these two are closely related to each other. There is lemmatization. This lemmatization assigns a root word, right, to just reduce the vocabulary size there. For example, if you see here, the lemma of was is B. Similarly, the lemma of is also B there. And the lemma of rats is rat. Similarly, lemma of runs is run. And wrote, written, all these lemma is their right. Thereafter, you will be also learning sentence boundary detection. Let's say if you have given a paragraph, how would you identify that? How many sentences are there? Thereafter, you will be also learning in coming lectures in a Spacy like what is a named entity recognition. With the help of the named entity recognition, you can label words a real world object. I mean to say that, let's say if you have given a sentence, in that sentence, you can label words with a real world object. Like if it is a person name, company name, location name, or it is a number, or it is a currency. There is then entity linking is also there. So this one comes from like let's say you have a knowledge base, and in that knowledge base you want to identify the entities. For example, you have a knowledge base of the entities, and new text data comes. In that new text data you can identify the words and how these words are related to the entities which is already in our knowledge database. You can also use a Spacy to find out the similarity between the words, similarity between the sentences, documents, or paragraphs there. You can use Spacy as a text classification as well there. You can use rule-based matching. This rule-based matching is like regex matching there. And later on you can also do, of course, if you are doing a text classification, then of course you can do the training. But the mean of training is here like the statistical model, the model which are doing the tokenization, parts of speech tagging, dependency parsing, all these models, you can train those model on yourself. Let's say if you have a custom data and you want to train your Spacy model on your custom data, you can train that. And then of course there is the serialization. That's mean if you have an object, a Spacy object, you can save those objects as it is as well there. So to get started with the Spacy, you need to install the Spacy. These are the commands to install the Spacy. You can visit this website here as well, spacy.io uses there, and you can select here the operating system. What type of operating system do you have? If you are trying to install it on your local computer, you can select either one of these. And if you are using here a Colab, then you can select a Linux, because Colab have a Linux operating system. And apart from that, if you are using M1 based Mac, then you can select platform as ARM M1, and thereafter you need to select here either Conda or PIP, or if you want to build it from the source. I would not recommend you to build it from source. You can select here PIP. If you have a Conda, then you select here a Conda. Apart from that, if you want to use here CPU and the GPU, let me tell you the difference here. CPU will be used for the most of the things other than the text classification. Although you can use the CPU for text classification, but CPU is not recommended because CPU takes a lot of the time to process there. So I would recommend, if you are planning to do like text classification or the training of the transformers there, then you should select here a GPU. And of course, apart from the GPU, then you have to also select your CUDA version here, right? So you select your CUDA version as well, what CUDA version you have there. All right. And then other configuration you can select. In coming lectures, I'll be showing you how you can select and install these. So the currently which you are seeing here, which I'm going to install here, pip install setup tool wheels, you see there. This one is the first, which will actually upgrade your pip and setup tools apart from wheel as well. I select here a Linux. I'm going to install it with 86, that means 64-bit architecture. I'm going to also select here a pip package manager, and then I'm going to select here a CPU. All right, I'm going to select here English model. So this pipeline is there, and now you see here the two things, either efficiency and accuracy. What are these? Efficiency, which runs very fast on a CPU. Accuracy is something their TRF. Do you see this? This one says that transformers. So transformers are slow on the CPU, but they are more accurate. Since this is tutorial, I'm going to use here efficiency, but do not worry about that. You can use anytime this TRF as well. The code will be exactly same. There won't be any difference in the coming codes. So you can use either of these models. So I select these. So I need to install these three. Now you see there, you have pip install setup tool wheel and pip install Spacy. This says that if their Spacy is installed, just upgrade this. And then once Spacy is installed, then download this language model. There are 3 different type of language model is there. So let me just in meantime run this, so it will keep installing it. And in meantime, I'll tell you 3 language models here. So those language models are core WebSM. This one is a small model, and then we have here large model as well. One is a medium model, and thereafter we have here large model, which is LG there. So these 3 model we have actually in our Spacy. Okay, just let me bring it here. So these are the 3 model in a Spacy which we can use. So this SM model is the smallest model, and it has a very limited set of the features. Moreover, I can say that all the features are available, only vocabulary is limited here in this case. And also the vector is also there limited. And if you want to do like the similarity, vector based similarity, then I would recommend you to use the large model there. All right. So this Spacy is installed there. The latest version of Spacy is 3.2. And now you see there, this has uninstalled Spacy 2.2, and it installed, latest Spacy here, 3.2.4 Spacy. All right, let me just clear that. All right. So apart from that, the Spacy feature is here. This one feature we are going to cover here, linguistic annotation. This one is the one of Spacy features. You see there, you don't see their linguistic annotation features, because this linguistic annotation is like the combination of parts of speech, lemmatization. I mean, all the features of Spacy there. All right. So this one is quite the beginning of the Spacy. I'm just going to show you how this overall Spacy starts from here. So you need to first import the Spacy as it is, and thereafter you need to load a Spacy there, and then it returns there a small model of the Spacy. Alright, their small model is returned, and once this Spacy model is returned, you know, this one is known as language object there. Now this text is going inside this language model, and this language model will do the tokenization here. And once all the tokenizations are, and NER, you know, I told you that this tokenization, NER, and parts of speech dependency parsing happens here inside this. Thereafter you can use a for loop for this doc object to get the original text data as it is. If you put there a text modifier there, so token.text, this will be returning here original data. Apple is looking at buying UK startup for $1 billion. And then there you say there, it says that the parts of speech there. And then this token dependency says that this one, how this is dependent there. All right, perfect. So let's just run this, and then you will see here all these results will be displayed there, right? Do you see there? All these results are here. So you might not be aware with all these terms. Do not worry about that. In coming lectures, we will be covering in details what is the parts of speech dependency parsing and the tokenization. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In a previous tutorial, we took the introduction of Spacy. We also studied what are the features of the Spacy, and we also learned how we can install the Spacy. We also discussed these are the language models, English language models for a Spacy. And then finally, we took an example of linguistic annotation there. And this was a very simple annotation, although you were not aware how all these annotation were done at that time. But as I promised you, in coming lectures, I'll be telling you how these linguistic annotations are done. So in today's tutorial, we are going to talk about the tokenization. So doing this linguistic annotation, the first step is tokenization. First tokenization happens, thereafter a tagging happens. That's you see here the parts of speech tagging, which I told you that we will study in coming lectures. But this lecture is only for tokenization. In coming lectures, we will be also doing tagging and the parsing. And now you see there, this one says that the dependency parsing, and then thereafter NER, and so many other pipelines are there. So this one is Spacey pipeline here. When you pass a text data, this text data are processed inside a Spacey language model in general, which is called as NLP. Inside this NLP, these are the Spacey pipeline. This tokenizer Spacey pipeline is default pipelining. This cannot be disabled. Rest of these pipelining tokens are components, you can say. These are pipeline components. So these pipeline components are optional. If you don't want tagging, parsing, and NER, these can be disabled. But by default, Spacey takes these components as enabled components like tokenization, tagging, parsing, and NER. After doing these language model tokenization and tagging, all these things, a doc object is made. So this returns a doc object, and then rest of other tagging, we can actually rest of other components value we can retrieve from the doc object. So this was about the previous tutorial which we did. You can find out the link of previous tutorial in video description. Since this doc object is now produced, now in this doc object all the informations are available there. Now just for the example, let's take here this sentence for the tagging or for tokenization actually. Since this is for tokenization, we will be focusing on tokenization. So this sentence, let's go to NY. All right, let's go to NY. This one is one sentence here. It says something like text is equal to, okay, it says like this. Okay, so their double quote is also included in the text. You remember that if we don't put here a single quote, then this will not, double quote will not be treated as a character of the string. So here it says that double quote. All right, then again here a single character comes. So for that, what we can do here, we can keep here maybe 3 character perhaps. That would be better to do here. Okay, so it says that here, let's go to ny. This one is your text data. All right, so in this text data, now we want to do a tokenization here. All right, although we don't want that new line as well, so we can simply do something like this. All right, so let's go to ny. All right, so for this we need to do the tokenization. The problem is here, you need to understand how this tokenization happens. By default tokenization happens with a space, but Spacy have a special features where it can actually break the sentences based on the prefix, suffix, and some infix and some exceptions. So these exceptions are language dependent. In English, we have some exceptions. In Arabic and other languages, there is an exception model for the Spacy. So this exception is a special case in English language there. So first it takes the, let's say this is the let's. So in let's, it find out that there is double quote, which is a prefix of the let's. So it break down that here in a new token here. Thereafter, it break down this let's here, and it find out that this one is the exception here. All right, so this one is exception, and here this one is exception. These two are exception. Now you will find here there and there, these are exception here. So this let's are broken into a 2 word here, let and apostrophe s here. Then go is pretty much simple, to is also simple. All right, and then this one is copied as it is. Now it is gonna break this one. Now you see here double quote is there. So this double quote as a suffix, first this was broken here. Thereafter you have n dot y dot and then this exclamation mark here. All right, so there this suffix is again broken out. Now you have ny here, and then this one exception happens here, and then this exception happens, which says that okay, now this ny will be as it is. The reason of keeping this is like how this Spacy is trained. So we know that UK, if UK is written there, u.k. that's the UK. Similarly, USA can be written that there, or UAE can be written there, and NY also can be written like this here. So it will take these as one word as it is. It will not break these words, because Spacy knows while training these are city name and these are the special exception where it will not break it. But at the same time, it will break here this let's here with these infixes here, because this one is here infix here. All right, perfect, cool. Now let's go and create a Spacy model and do the tokenization of this text, and then see how we are gonna get the result. So we will be first importing the Spacy. Of course, you have to have a Spacy, so you have to install the Spacy here like we explained in a previous tutorial. Once you have a Spacy, then you can just simply import a Spacy. Once a Spacy is imported, now we need to make here a language model. So the language model is NLP equal to Spacy dot load, and there we are gonna load here English model, en core, we have web, and sm, that's the small model. All right, a language model is created, English language model with a small model. It is created here. Thereafter you have doc is equal to NLP, and then we are going to pass this text data here inside this. So once we pass this text data, because we created this default language model, it automatically have all these pipelines inside this. So as soon as we passed here doc is equal to the NLP text, all these pre-processing happened instantly inside this Spacy language model. Once you have this language model, now if you print this doc, you will get the text data of the doc itself. But if you want to get the tokenization for each words, for each of these pipelines, then you need to do here a for loop. So for token in doc, this is gonna give us a token for each word, for each of these words here. Then you can simply do here a print token dot here a text here, right? So like you see here, this is how it was broken here, and the same thing we saw here. First this double quote comes, then let comes, and then finally apostrophe and s comes here, and then similarly go to ny, and then here exclamation mark, and then double quote. All these are broken in a single character, not a single character, but in a single token. So that's how this tokenization happens in a Spacy. In meantime, you can also try some some other text as well. Let me just show you. I just copy this text from there, and then this language model is already created. You don't need to recreate that model again, but this doc is equal to the NLP text, and then let's do this one. Thereafter I'm gonna just put here some other text here. Okay, let's put it, since now we don't have any special character, so I'm gonna just use here a single quote here. I'm gonna say here Apple is looking to buying UK startup for $1 billion. All right, that's how. Let's do the tokenization and then see how this happened here. This Apple is looking to buying, all these are pretty much simple, and that's what we were talking about. Their exception happens while the tokenization. Now as the language model was trained, it knows that this UK is a geographic location. That's when this is a country name, so it kept here UK as it is. Thereafter you have a startup for $1 billion. Now you see this dollar was broken. That's mean because this one is a currency here, and this one is a number. Again here, this one is like a currency measurement, or you can say the measurement unit. This one, billion, is there. Now again, if you put here a dot, now you will see this dot will be separated there, right? But this dot was not separated, because like how this Spacy model was trained there while creating this Spacy. All right, cool. So in the next lecture, I'll show you how you can do the parts of speech tagging. So do not worry about the first lecture where we studied linguistic annotations, because in the coming lectures, we will be covering all these one by one. All right, thanks for watching this. Stay tuned for more videos. Hi everyone, welcome to Spacy Masterclass tutorial. In previous tutorial, we have learned introduction of a Spacy and tokenization using a Spacy. In this lecture, we are going to study parts of speech tagging and dependency parsing. After tokenization in a Spacy, Spacy actually parse and tag these components. In a previous tutorial, you learned this. After once we pass these this document or text data, it does the tokenization here. After this tokenization, tagging and the parsing happens, and thereafter NER happens. This is the default pipeline of the Spacy. If you have not watched previous video, you can get the link in video description. Go and watch that video there. All right. Thereafter doing this parsing and the tagging, this NER happens. But you know how these parts of speech tagging and dependency parsing happens here. There is a binary model in a Spacy, which is pre-trained model. Okay, that pre-trained model is these models, like these EN Core Wave SM. This one is the pre-trained model which we download from the Spacy. And there is medium and the large model is as well available at the Spacy there. You can download these English language model to do parts of speech tagging and the dependency parsing. So what are the attributes you can access from the parts of speech? Actually, you can get the list from here itself. You just open this here. You get all these documents you can access from this doc object, which is produced by this Spacy. Once a Spacy runs, then it produces this doc object. This doc object have these attributes you can access from there. All right. Now, do you see here there are two duplicate names? Seems like, because there is a name and then the same name with the underscore. Okay, so this name is actually a hash value. Like every other NLP model does the hashing there to make it faster and save some memory. Spacy works in that way as well. All the tokens, all these tokens are stored in the hash value. If you want to access the actual value from the Spacy, then you have to put there the underscore value there. Alright, so enough of the talking. Let's go ahead and see how these parts of speech tagging and the dependency parsing happens here. Well, as usual, you need to install your Spacy with these three commands. You install a Spacy, its setup tools, Spacy, and then you download this English language model there. Thereafter, you do here import Spacy. All right, so this imports Spacy, and thereafter we are gonna create here an NLP object here. Then I say here NLP is equal to Spacy dot load, and then I'm gonna load this particular model. All right, so this one gonna load that model. Once this model is loaded, this one is a language model. Now we are gonna get the document. So our original text data is this one. People is looking at buying UK startup for $1 billion. This one is our text data. Now we are going to get the object from the NLP language. We pass our text data in this. All right, now you see, as previously in our first video, we got here this linguistic annotation. In that linguistic annotation, we accessed those attributes which we were seeing here. These attributes we access with the underscore. There are many attributes are here, maybe perhaps 50-60 total attributes are there. So these attributes you can access from that doc object, this doc object which we just produced here. All right, in this doc object. So this object is actually the tokenized here. There are the multiple tokens here. And if you want to access the objects for each of those tokens, you have to iterate this doc object. All right, so we want to also print this doc object in a nice and tabular format. So what I'm going to do here, I'm going to install a beautiful table here. So I need to write here pip install beautiful table. All right, just install this. Once it will install, I'm just going to clear these outputs to save some space. All right, then I'm going to do here from beautiful table import beautiful table. All right, so this table is imported here, and then I create here table is equal to a beautiful table. This one is an object of the beautiful table. All right, once all these happen, now it is time to iterate this doc object to get these components. That's mean from this text data we can get all these tagging or the text documents from there. All right, I'm just going to add few cell here, just add code there. Then what I'm going to do here, I'm going to add here this table dot columns dot header So this one is gonna put the header of table there in the column value. There I say first is gonna be a text. Thereafter, I'm gonna put here parts of speech, POS tag and dependency. POS. Thereafter we had this tagging value there, and then we had this dependency parsing there. There are other attributes as well, like the shape attributes. I'll show you in that attribute list what is this. And we are also going to access from here is alpha attribute. And thereafter, this is alpha says that whether a particular token is alpha value or is it numeric or alphanumeric there. All right, so that says that is alpha. And at the same time, we can also get here is stop word. That's when is stop means if a particular value is a stop words or not, like these are the stop words there. All right, so that's how I got this table column dot header, and then I can simply go for token in doc, because this doc object was actually tokenized into a multiple tokens. If you see this previous example in last tutorial, let's say this was the text data. Let's say if this was the text data, it was tokenized here into a multiple tokens, right? These are the multiple tokens. So the same thing happened here. This particular data is analyzed into a multiple tokens, and those tokens we are going to access by iterating this doc object. All right, then I say here table dot rows dot append. All right, so we are gonna append these values into rows so that we can show it into a tabular format there. I say token dot text, that's the original document here, the original text data. Thereafter I say here token dot POS underscore, that's the parts of speech here. All right, then I say here the token dot tag underscore. Then I again say here a token dot dependency underscore, that's the dependency parsing there. Then I get here token dot shape. Then again I need to put here underscore so that I can get the text value. Then again token dot is alpha. All right, so is alpha actually don't need here any underscore because it's already a numeric value. Ones and zeros are true and false, you can say like that. So there is no text data, so you can consider that it is in the same format. There is no need to put there underscore. And similarly there token dot is stop. Now one thing you always need to remember, the number of headers here you have to match these number of fields here inside, otherwise it will throw the error. So whatever the header you put here, you have to put same number of values here, otherwise you cannot keep larger or lesser rows column than the all other rows. All right, so I just run this. Thereafter I'm just gonna print this particular table here. All right, now you see this is a very beautiful table printed here, and overall text data which we had, that was Apple is looking at buying UK startup for $1 billion. So this text data is here. Apple is looking at buying UK startup for $1 billion. The parts of speech says that this one is the proper noun auxiliary, and now there is the verb, and then the verb, proper noun, all these things. Although the sum of names actually I don't remember. I'm just some of these names I think I'm missing. You can get these names from here. Universal dependency POS. You just need to open this link from here. You get all those values which we are missing here, right? I think it was what was that, ADP, that is here, this one, right? You can get there. This one is at position here, is a cover term for the prepositions and the post positions. This one ADP. All right, although if you want to know at the shorter format here, you can just get it from here, like at position, all the I mean to say that actual name of the shorter format is here. This proper noun, punctuations, all these here. All right, then the tagging says that here how these words are actually dependent on each other there. If you want to get the details of these tagging, you can get these details from this link here. I'm just gonna paste this link there and here as well. All right, let me just put this link here. All right, so there we have this whole tagging, a detailed tagging. I'm just gonna zoom it. Now you see there we have this tagging is actually a detailed parts of speech explanation there. That means how this parts of speech tagging works there. So like we have for this apple, we have NNP. That's when now you see here NNP is noun. This one is a proper singular noun here, NNP. And the example of a proper singular noun is like, Germany, God, Alice, all these are proper singular noun here. And similarly, we have here, VBZ. VBZ is somewhere here. You see, this one is the verb, third person, singular present. Now it's like see things or something like that. Now you see there, there is this one. And then we have VBG there, right? That's when we have this one. Verb, gerund or present participle, like thinking is fun or something like that, right? Here we have looking and there is the thinking or something like that. This one is interjection here. You see there, IN, that's that one is here. This one is conjunction actually. So there you have a conjunction like off, on, before, unless, in, all those. So this one gives you a detail, exact parts of speech tagging. And this one says that as the overall parts of speech, and this one tags a particular form of the parts of speech there. All right. And then dependency, this one says that how these words are related to each other, right? So dependency is actually this syntactic dependency is a relation between the two words in the sentence in which one word is governing words, another one is the depending words. So what happens here, it says that the root, that's mean it says that this one is a word which is actually making some action here. This one is the root word. All right. And this one is a noun there, a subjective noun you can say. So this apple is subjective noun there, and the action is being done like looking. All right. The action is being done as the looking, and rest of other dependency here. We will take another lecture where I'll explain you how these dependency are work together, how one words are dependent on the another words. All right. So the next lecture maybe will be based on these dependency parsing specifically there. All right. So thereafter we have this, the shape is there. So in this token you have a shape as well. Maybe we can search this. All right, so their shape is, it says that transform the tokens string to show orthographic features. All right, alphabetic characters are replaced with either small x or capital X. If number is in a capital format, that will be replaced with the capital X. If it is in a small format, then it will be replaced with the small x there. And if it is number, then it will be replaced with D there, a small word of the D. Now you see there the same thing is happening. This one is form of 5 word. Now you 5 character. Now you see the shape says that total 5 X are there. One capital X says that the first character was in a capital letter. Here all character and the rest of other characters was in a small letter, and there we have a capital letter. Then again this one is the currency. The parts of speech tagging for this currency is a symbol there. And then of course this one is the number there, and this one is also represented as a number there. All right, and this number is represented as a D in the form of shape. And this one says that whether this particular token is completely alpha token or not. So it says that yes, this one is the alpha, all these are alpha, but this one is not the alpha token, because there is this one is kind of the mix of the tokens with the dot and this one. So there is the special characters inside that. Then of course these are the alpha tokens there, but these two are definitely not the alpha tokens. Similarly, it says that is it a stop word? So one means yes, it is a stop words. In English language, there are words which are quite repeatable words. Those are stop words. Like is, for, at. All these are stop words there. This one is the at. I mean to say that the words which doesn't make much sense, and which gets repeated multiple times, those are placed as the stop words in the English. You can simply search here stop words in English language. So you will get here these, you can open any link actually from here, whatever the link comes first to you. You can open, no, this is not there. Maybe here you can open. Does it have? No, it don't have, I'm sorry. Yep, let's see here if it has. All right, so NLTK have these stop words. All right, so these stop words are repeated, quite often. So the words which are repeated quite often in literature, those are considered as a stop words. So yes, of course, this one is repeated quite often in literature, so it is considered as a stop words. This one is also a stop words there. All right, so that's how you can do the parts of speech tagging. And in the coming lectures, I'll be talking more about the dependency parsing, how one words are related to another words. I'll be showing you how these root and the subjective nouns are correlated to each other, and other than that, like preposition and other dependencies, other tokens are dependent to each other. Thanks for watching this video. Stay tuned for the next one. Hi everyone, welcome to Spacy Masterclass tutorial. In this lecture, we are going to visualize dependency parsing. In last lecture, we saw how we can do parts of speech tagging, and at some extent, we also saw dependency parsing there. At that time, I told you that in the next lecture, I'll cover dependency parsing in the detail. The last time we took an example text data. Apple is looking at buying UK startup for $1 billion. And we saw that a dependency tagging was something like that. Let's go ahead and print this table once again. Now you see there, we don't have any explanation, but here I want to put explanation of these tagging. So what you can do here, you can do actually like, explanation, you can say that explain it, right? Explain tag, and after this tag I'm gonna just put here a new part which says that Spacy dot explain, and inside that I'm gonna say here token dot tag underscore, right? So this one is gonna explain this. In fact, I should be doing, this table should be first created. Thereafter, I should be doing this. And then I should be, printing this. So here you have got the explanation of these tag. This says that this one is a proper singular noun. The last time which I had shown you here, noun, a proper singular noun. And now you have it in this explain tag here itself, right? All these you can understand here. It has a symbol and currency. This one is the cardinal number, and here again this one is a cardinal number here. All right, so let's go ahead and understand this tagging and dependency, actually how the words are dependent to each other. So you need to first understand what are these dependency. Dependency parsing is the process of extracting the dependent words from these sentences. So here we have one root word. The root word is known as a head word. So root word is not the dependent on any other words. All right, so this one is the head word. You can say like if you search here dependency parsing and you go inside this image here, you will see some images like these. There you see a root is there. That means that is the head word. Some similar thing you will get here. So the head word are not dependent to anything, right? So there, let's say you have, so at the top you have a root word and then the rest of the other words. This is that how these words are the dependent there, here and there. All right, so that's what we are gonna visualize here. But first we need to import, a Spacey here. So Spacey, which is gonna display a Spacy dependency inside our notebook here. So I'm gonna do here from Spacy import Spacey, right? So Spacey is a tool inside Spacy which will be displaying the dependency something like this, right? So it will be showing us total graph of the dependency between the words here. All right, so it's very much simple. It's very much simple to display it here. You can simply write here Spacey dot render. If you are using a Jupyter notebook, you write here render. Otherwise, you should write here serve. That's mean if it is a proper Python code there. So Spacey dot render. Inside this, I'm gonna put that doc which we created in our last lecture. So there you have, this doc is here. Where is that? Yes. So this doc is here. We are gonna create, we are gonna pass that document here, doc object you can say, and the style which I'm gonna, parse here. I mean, the style which I'm gonna display here, that is the dependency. That means that is the dep. Just run this. Once you run this, you get something like this. Maybe, well, this is not displaying it here. I may need to check this once again, how we can display this perhaps. Well, so this one is serving at this, since we are using here, Colab notebook. So definitely we cannot do this. This should be render here itself. Just give me a second, I'll check it. Well, I think I need to pass here one more parameter which says that here I'm using a Jupyter notebook. There I should be saying that make it as a true. All right, excellent. Now here it says that I'm using a Jupyter notebook and it has displayed our dependency in a very nice, chart here. And again, it is saying that this looking, now you see there, earlier we saw that this looking was a root word, right? Do you see that? This looking was a root word. That's why, everything it says that how the things are dependent with this root word. So this proper noun is completely dependent with this root word. This one completely says that, okay, this apple is looking for something which is dependent on a startup here. Do you see this one? So this word and this word, these are the most important words are here which we can say, and rest of other things are getting dependent on this particular number, the billion. All right, so this overall says that how important these words are here inside this. If you want to study this in a more deeper way, you can visit this particular link where you will find out these dependency parsing manual here. So it's a PDF. It has a very detailed description of all these dependency parsing techniques here. It's a 28 pages document. If you are doing a research in machine learning, especially in the field of natural language processing, I would suggest you should go through with this document to have a deeper understanding of the dependencies here. All right, now let's go ahead and see what are the other options we can pass inside this Spacey so that we can render our this graph in a more better format. All right, so I'm going to put here like options. So the options are actually a dictionary here. Now we can pass here this dictionary, like I have here this compact. If I want to make this compact is equal to the true, then I should be doing like this. And apart from that, I should be also passing here this dictionary as the options is equal to options here. All right, just run this. Now you run this, you see there I said compact is true. That means this one is a compact representation of this document. Even you can set its overall overall width as well. That width you can pass here the parameter which is known as distance. So let's say if I'm gonna say here distance is 90, so it is now reduced to perhaps the 90%. If I say the 100, that's mean it will be utilizing almost the 100% area here, right? So perhaps this one is the better option to use here. You have more options, like you can change the background colors. You can also change, these lines color. All these things you can change here. Let's say if I want to say that I want to keep background color here, that's the BG. So in the BG we need to give hexadecimal colors there. Let's say I say cyan hex color. What is cyan hex code? So cyan color hex code is like this, right? Do you see this? Cyan color is like this. All right, so I'm gonna just get this whole hex color from here. You can take any any color. I'm just gonna pass this. Now you see there, this one is there, cyan hex color. If I want to put here a more deeper color, I can give here perhaps a more, I can increase these values perhaps. All right, so it would be giving us a more deeper color here. All right, perfect. Maybe this was better option perhaps if we put something like this. No, just a second. Oops, nope. All right, perhaps this color is okay, seems like. All right, now let's go ahead and change the font color as well. You can choose any colors as per your choice here. Okay, so for a font color, I mean for these forehead color, you can choose their color. You can also give the name. Otherwise you can also give this hexadecimal value as well. Like let's see, if I want to give the white color, you have to put all these values at 6F there. So you will be getting these as white color. But let's say if you want to make it as a gray color, you can simply put there D like this something. All right, so although this one doesn't seem pretty much visible, so what I can see, I can do here dark color hex code, right? You just search it here, you will get some not every dark, but maybe perhaps I would like to put this color or this color maybe. All right, so let's go ahead and choose this hex color from here, and then I'm going to put that hex color as the BG so that we get better contrast here. All right, so we have got here a better contrast. Now you can also change this font as well there, like you can put here the font here, this font as I'm going to put here Source Sans Pro. So it's going to use Source Sans Pro font here. All right, so all these options you can try on with the dependency parsing, and if you want to have a deeper knowledge of dependency parsing, then I think you should visit this document. If you have not watched previous videos where I have covered introduction of Spacy, tokenization, parts of speech tagging, and the introduction of dependency parsing here, I think you should visit previous videos. The link of previous videos are given in the description. All right, thanks for watching this video. I'll see you in next lecture. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, we are going to study how you can identify sentence boundary using a Spacy. In previous lectures, we have seen how Spacy do the tokenization, parts of speech tagging, and dependency parsing. All these things we have seen previously, but we have not seen if a paragraph, I mean to say that if a text data is a paragraph. That means a paragraph have a multiple sentences. So how these multiple sentences are divided into the sentences, and then parts of speech tagging and the dependency parsing is done on the sentences, individual sentences. All right. So here I have taken this example paragraph. This paragraph is recent news, which says that tap to pay on iPhone is set to compete against the existing iPhone payment systems. Then it will let small businesses accept NFC contactless payments through the supported iOS app. Alright, so all these are paragraph is consist of sentences. Alright, so overall you can say the sentence detection or sentence boundary detection is the process where you locate start and the end of the sentence there. This will allow you to divide these sentences, these paragraph into the sentences where you can do the parts of speech tagging, parsing and dependency parsing, NER extraction, all these sentence by sentence. Alright, enough of talking. Let's go ahead and starts doing sentence boundary detection. So first of all, as usual, you have to do the import Spacy. If you are watching this video in continuation of previous videos, then you may not need to do this one. But if you have stopped this video previously and you are starting this lecture on a new day, then of course you need to do this. Thereafter, as previously we have been doing here, you can load your Spacy English language model there in a new term, which is a new object, which is NLP there. Alright, so this object is loaded there. Let's go ahead and get the doc object. So I get here a doc object is equal to NLP, and inside that I put my paragraph sentence here. Alright, this whole paragraph I put there. So now I got here a doc object, Spacy doc object. Now you can get original sentence if you just print here this doc. Otherwise you can put here dot text. There you will get this original sentence there. Alright, this one is in encoded format. Otherwise you just put it here a doc, this whole sentence will come here. But if you put here list, alright, since this one is iterator, that means it is the it has so many tokens and the sentences. So if you do here like list, you will get all the tokens in the form of the list. Do you remember previously we did there the tokenization, something like this? So you are getting not like this, maybe sometimes back we did that. Alright, that's linguistic annotation. Here this one is the tokenization. So that was the text token, then like that. So all the text was divided into individual tokens. That's what happened here. If you just put there list and doc, right? Here a for loop you don't need actually. And you can also do it like here, sent. You provide this sent, you will be getting hash value here. Since we actually don't need these, sorry, it's cents actually. This is sentences, that's cents here. All right. So these are the sentences. Now do you see there? These are the sentences here. All the sentences we are getting here. You can say like this, cents, and then you can get here the length of the sentences. So it divided into a length of 3 sentences there, and simply you can do like this for cent in cents. All right, then you just print here this sentence here. All right, so it says that it has one sentence here, this one considered as one sentence. Thereafter there is another sentence, and there this one is the last sentence. You see here a new line because I had given here a new line so that you can see this whole the paragraph there. Otherwise, if it is like a raw text format, then of course it would be something like this, a straightforward one paragraph. You just simply run this once again, all this, and now you will see here clearly just a 3 sentence. So the first sentence is this, another one is this, and then the last sentence you have this one. Now based on these sentences, you can like in a previous lecture we did our the dependency parsing and rest of other things you can do now, the sentence by sentence, right? Do you see there? This one is considered as one sentence. If you put everything here in one code, then you take this one sentence at a time, and then you do your parts of speech tagging and dependency parsing sentence by sentence. All right, perfect. So this is all about in this lecture. In the next lecture, we will be covering what is the stop words. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, we are going to cover what is the stop words. In previous lecture, we cover what is the tokenization, sentence detection, Spacy installation, and the use of Spacy in natural language processing. In this lecture, we are going to cover stop words. Stop words are the most common words used in a language. If we talk about the English language, then English language, the stop words are like, are, but, they, is, the. All these are stop words. So when words are used frequently in a sentence, those can be considered as stop words. So these are like a standard stop words, but it's not like any mathematical formula that it will be always a stop words. Depending on your use case, you can define a set of words which acts as the stop words. The sometimes removal of stop words helps you to improve your machine learning model, but sometimes it don't. The reason is here, stop words helps you to set the context of the sentence. For example, let's say if I talk about, let's say if I talk about I am eating. All right. This one is one. Otherwise, I can say that another sentence is like, I was eating. All right. So these two sentences. Let's say if I remove a stop words from this sentence now becomes I eating. All right. And at the same time, if I also remove a stop words from here, this become I eating. Now you see there, the final result is ambiguous here. We don't have any context here. All right. Although the grammatically it is also incorrect here, but if we leave that there, even after that, this one doesn't make any sense. I mean, there is no context. Here it was saying that something is happening in presently, all right, currently. And this was saying that something happened, sometimes back. But if we just remove these stop words, it doesn't give us any context when and how this happened. That's why sometimes having these stop words help you, and also sometimes it also help you to remove this. For example, if you are making some machine learning algorithm, which is being actually, skewed toward these stop words, especially in TF-IDF algorithms. All right, this we will be covering later on coming lectures. So in TF-IDF algorithms, it actually calculates the term frequency. So stop words frequencies are always high. So if stop words are always high, so these will be coming at the top. And in general, stop words doesn't make sense as a individual words. For example, let's say if I tell you to consider I am, was, and then eating. Just consider these as a standard word. All right, a single word. All right. So this makes sense that, okay, this one is something referring with me. I don't think this makes sense as individual word. I'm saying that as individual word, there is no meaning for these two words. And this one also saying that something is happening. That's the eating. All right. So when you try to get the context of individual words, then these stop words does not help you. All right. So these stop words you can get from Spacy automatically. In previous lecture, we installed Spacy and imported Spacy. I'm just going to show you again here. You just import Spacy like this. And thereafter you load Spacy NLP object, something like this. So there you see NLP is equal to the Spacy.load EN code. That's the English language core model, small size model. We have three different models there. One is the medium size, another one is the large size. Just run this and NLP object is created here. At the same time, you can also get here from Spacy the stop words as well. So like this, let's say I say here stop words is equal to Spacy dot language. I'm referring here English language. Thereafter I want to know here these stop words. All right, and then in this stop words it has a variable named as stop words. So this one gonna give us a default value of the stop words. Again, I'm saying that there is no mathematical formula to decide the stop words. This is completely up to you where you are using these stop words, whether you want context or not. So you can set it accordingly. Now you see there a stop words list is quite high here. All right, because the sentences on which the Spacy was trained, there these words were occurring so often there. All right, that's why these words were considered there as the stop words. But in general, if you see there in these stop words, there are many words which could be important for you, like something this again, maybe. Okay, I mean, any of these words can be important if you are trying to get the context of the sentence as well. All right, so where you want to predict the context, then I would recommend you to keep the stop words, although you can test your model with the stop words and without the stop words. Now let's go ahead and filter out stop words from these sentences, from this document. All right, so it was the para document there. So from that, the para document, that's the paragraph. From this paragraph, I'm going to filter out I'm going to just filter out those stop words from here. So basically what I can do here, I can just say something like this: for I just need to actually go in the one by one token there. So I say here for sent in cents. All right, this was the sentences there, and then I print here this sent there. All right, this was the sentences. This one is the single sentence. All right, here this was single sentence and this one is single sentence. Now let's go ahead and get again doc object here. I say here doc sent is equal to NLP, and for this particular sentence I'm gonna get the doc object. All right. Let me just check that if this is already, this one is already, yep, this already contains as doc object. So basically you don't need to print that, you don't need to get the doc object again. You can just say that for token in this sent. All right, now you can print these token. I'm just going to put here a break so that it can just run for a single sentence. So this is running on the single sentence here. Single tokens are broken out here. So what I'm going to check here, if token not in stop words. All right, so there we have the stop words. Then we need to print our token, and then let's see what it says. It says if token dot text not in stop words, then just print the token. All right, so it's getting this text data from the token, and then it is checking if it is not in stop word, then print. Now you see there 2 is removed from there. In this sentence 2 is removed. Pay iPhone set complete existing iPhone payment solution. Now you see, I was saying you the context. Do you see here, if you read this sentence and this sentence, which one is making sense to you? I believe that this doesn't make a sense to you. Let's say if I just do not print that sentence and you see this whole sentence. If you read this now, this sentence doesn't make much sense there. Like tap, pay, iPhone set, complete existing iPhone payment solution, merchant square. So this seems like a disconnected individual words. By reading these as a human, you may not be able to get the context of the sentence. That's what I was saying, that sometimes keeping a stop words help you, sometimes removing a stop words help you. Alright, in coming lectures, sometimes we will definitely discuss these stop words when we will be writing machine learning algorithms for classification of the text data. Alright, thanks for watching this video. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, we are going to cover lemmatization. Lemmatization is the process of reducing inflected form of words while still ensuring that the reduced form belongs to the language. Moreover, I want to say here, when you are doing natural language processing, you have a variety of words which is derived from a single word. You can reduce those to its root form to reduce the dictionary size. The reduced form of the actual word is known as lemma. For example, if you take these three words, playing, plays, and played, all these three words are derived from a play word. So this play is actually a lemma of playing, plays, and played. As usual, we have been installing our Spacy before starting the lecture. So the same thing we are gonna do here as well. Just for a quick recap, I want to show you, you need to select runtime. Actually, you don't need to select runtime. If you are doing any GPU or machine learning, then you need to select GPU or TPU, otherwise it's okay. You can only run this. It will automatically connect to a free machine at a Google Cloud server, and then it will install Spacy and its other relevant libraries at your Google Colab. If you have already installed this Spacy, you don't need to install this. Since I'm beginning this tutorial after a day or two, so the last time when I was going through other lectures like stop words, sentence boundary detection, visualizing, dependency parsing, while doing all these lectures, we had installed our Spacy in the same process as we are installing it now. Again, I'm telling you, if you already have it, then you don't need to install it. Since we are using here on a Google Colab, so every time you restart your Google Colab, you need to install these libraries. That's why I installed that. So I just deleted all the logs because this was installed in my Google Colab. Now, as usual, I can start with the import Spacy. So this is gonna import the Spacy. Thereafter, I'm gonna create here an NLP, that's mean a language object, NLP language object, Spacy.load. I'm gonna use here a small language model, English Core Web SM, that's mean the small language model. Since we are gonna find out the lemma of these three words, so we need to keep these three words in a sentence. I say here text is equal to playing, played, plays, and let's say take the play as well. So this is the text data. I'm gonna get here NLP doc object. So it's like this, doc is equal to the NLP text. Thereafter, we are going to use here a for loop as usual. So for token, and then for token, and thereafter we are going to take here, for token in doc. So this doc is actually a collection of tokens, and then we are gonna here print token dot text, that's been the original text data, and we are also gonna here print our token dot lemma underscore. So if we don't put the underscore, then we will be getting the hash value. So it's must to put there the underscore to get the actual text data there. That's all we need to get the lemma. That's all we need to do to get the lemma here. So what do you see there? We got here a played as the play, plays as the play, and play as the play, but not for the playing. So what happens in the Spacy? Spacy doesn't take these words as a single or independent words. it takes all these as a single sentence. So at this time it seems like Spacy has treated this playing as the noun. For example, let's say we have apple. In the apple, we have the apple as the organization and as the fruit as well, depending on where it is used. That's what here it is happening. So to just just understand this once again, since we know that played got converted to play, plays to play, and play to play, so we can remove at least one or two, because we know that for those it got converted to play. So we know here that for these, the lemma of these words are the play. Of course, play is the play, so that's the root form already. Let's go ahead and run this and then see what happens. This time this should be converting. No, this did not convert. So it's like playing played. It's like he played, or I played, or she played. It's something like that. So what I can do here, I can remove this as well. So it will be something like just the playing there, right? This one. Okay, let's run this and then see what happens. Yeah, cool. So this playing got converted here as the play. That's the, so you know what happened there. Playing played is like a similar form where we say that I played. So this I is here like the pronoun and something like that. This playing in Spacy is being treated as like noun or a pronoun. That's why this was not got converted. So when you want to get it converted into the lemma, the word should be playing as the verb in the sentence. That's why that did not convert it there. But let's say if I say here I was playing, maybe this should be definitely converted to the play, right? Because the was, the B form of this was, sorry, the lemma, that's the root form of this was is B, and the root form of this playing is the play. All right. So once again, let me recap what you learned today. The lemmatization is like the reducing the words into its root form. Why we need the lemmatization? Sometimes we need to do the text normalization. So the text normalization means you need to convert a various form of a single word into a single form. That's mean into a root form. So by doing that, you get the one word for a multiple word, ultimately that save the space and make the dictionary which is less in the size. All right, perfect. So there could be many other uses of the lemmatization as well. Apart from this lemmatization, there is another technique which is known as the stemming. So we will learn that stemming in the next lecture. Thanks for watching this video. Hi everyone. Welcome to Spacy Masterclass tutorial. In the previous tutorial, we have seen how you can do the lemmatization using a Spacy. And I told you that I'll take a lecture on stemming. Spacy does not provide any way to do the stemming. That's why we are going to use here NLTK for the stemming. Although this lecture is completely based on Spacy, but only for this particular lecture, we are going to use here NLTK. So the stemming and the lemmatization, moreover, it's a similar thing here. Like lemmatization reduces a word into its root form, the similar things is being done by the stemming as well. If you have a various type of the words and you want to reduce your dictionary size, you can use either stemming or a lemmatization. So this stemming reduces a word into its root word. But the difference between the stemming and the lemmatization, here you see in the stemming, the words which got converted into the root word, this word may or may not make any sense. But in lemmatization, there is always a word, to say that the word will be converted into some meaningful word. That means when you try to search these words into the dictionary, you will not find the meaning of these words. So the stemming does not preserve the meaning of the word, but it reduces a word into its root form. Moreover, you can say into a smaller form of the word where you can reduce the dictionary size. For example, if your sentence have these three words can be reduced to this a single word only, although this word does not make any sense. Similarly, a dictionary have these, let's say, the 6 word that can be reduced to only the 2 word here by using the stemming. And similarly, if you use lemmatization, you can also reduce these words into these single words, but those words will definitely make some sense. Let's go ahead and first test stemming. Thereafter, I'll show you lemmatization as well. So this NLTK already comes as the pre-installed with the Python. And if you do not have NLTK, you can install the NLTK with this command here. So we are gonna import here porter stemmer and word tokenize from the NLTK. So from NLTK dot stem import porter stemmer. From NLTK dot tokenize import word tokenize. PS is equal to porter stemmer words is equal to changing changes changed change. So the moreover this word I'm testing here. So these words I'm gonna just test how this word is going to be converted into its root form. So now I'm gonna convert this word using NLTK stemming. So for word in words, all right, thereafter I'm gonna print here first word, thereafter PS stem word. Let's just print this. Now you see these words got converted into its root form, although these words does not make any sense here. Let's go ahead and test this with a Spacy lemmatization. So as usual, we need to first import our Spacy and then we need to make here English language model here. That's the object Spacy dot load. I'm gonna load here English core wave SM, that's the small model. Once that is loaded, then I say here for word in words, for word in words, then I need to just here get a doc object for NLTK word. Thereafter I need to get the tokenization in doc object. Then I need to just print here first word, for which I'm doing lemmatization. All right, thereafter I'm gonna print here token dot lemma. So that's gonna print here word and its lemmatized word. So now you see this changing got converted to a change. So this change definitely makes some sense, although in the stemming this does not make any sense. There is another difference between this and that. That is, this one is a little slow than the stemming. So where your requirement is not the accuracy but the speed, you can use the stemming. But if you want word, root word in some meaningful word and speed is not your requirement, then you should use this lemmatization. For example, if I use here a magic word, time it, then it will time the total timing, how much time it's gonna actually take here. Okay, so it says that 58 millisecond per loop. All right, although it's a printing it is printing this, and at the same time if we do it here, this should be the much faster. So this says that the 3 millisecond per loop, and here it said how much it was. It was a 58 millisecond. Now you see the difference between lemmatization and the stemming. Although this is not accurate format to measure the speed, but in the real world, stemming is very much faster than the lemmatization. Alright, so this is all about in this lecture. Thanks for watching this. I'll see you in next lecture. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, we are going to see how you can get the word frequency count. Word frequency count can be used in various ways, like on a given text data, you can find out the frequency of the words, that's mean the most occurring words and the least occurring words. So the most occurring words, that's mean you can find out the common words in a given sentence. Alright. For example, let's say if I take some random text from a news site about the Elon Musk, I just took this one. I'm just going to copy this from there. And then I say here text is equal to, this text data. Alright, so that text data, I got it from here. If you want to see this text data as the wrapped format, you can see it here. Well, seems like it is not there. Alright, so it's not getting wrapped, but still you can read this text data. So we are going to find out here in this text data the most occurring words and the least occurring words. It's a very common process here. So you can say that from collections import counter. That's it. Thereafter, you can simply say that word frequency is equal to the counter, and inside that you need to pass your text data. That's all. Now you get here your word frequency. All right. So this word frequency says that there are a space 74 times, dollar occurs 1 time, and these are some random like well, seems like something is not correct here. I think I need to pass it into a form of list perhaps. No, it's not like that. I'm sorry. So this has to be splitted. So you need to just split it. Thereafter, you can get the word frequency. All right. So that's where that's there the word frequency here. You see there. These has occurred only 1 time in this whole sentence. Right. Although this list still goes on, but these occurred just a single time there. You can simply apply here dot most common. So you will be getting here the most common words. Maybe you can apply here a 5. So 5 times most common words you are getting here. So on is 3 times, deal 2 times, market, from, and the tech are mentioned here, each of these as the 2 times. That's how you can get the most occurring words here, the most common word. Now the another question you can ask here, that if you want to remove a stop words from this text data, and thereafter if you need to calculate the frequency of words, then how you can do that? Well, it's pretty much simple. You can import here a Spacy. Thereafter, you can make here the NLP object here is Spacy dot load. Then you say here en core wave sm. All right. So you got here the NLP object. Thereafter, you say here like the doc object is equal to NLP. and inside that we are passing our text data. So we got here the doc object. Thereafter I say here words is equal to, now I'm gonna use here a comprehensive list here. So there I say like for token in doc, if token, I need to check if token is not a stop word. So it's very much simple, like if token is not a stop words, then I need to get the token here. So I say the token dot text. So I say if token is not the stop words, and I also want to check token is not a punctuation. That's mean you will not be getting a punctuation counted as the most occurring word. That's how I get these words. Once you get the words, similarly you can say that word frequency is equal to like this. That's how you get, and then you can get the most common words from this word frequency. Now you will see this on was considered as the stop words. That's why it is removed from the most common word. And apart from that, you see there a from is also a stop words in English language. That's why this one is also removed from the most common occurring word list. Alright, so that's how you can use a Spacy, is stop and is punctuation, as well as how you can use collection and the counter. This is what you learned in this lecture. Thanks for watching this lesson. I'll see you in next lecture. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, we are gonna see how you can do a rule-based matching in Spacy. This rule-based matching in Spacy is a little different what you do with the regular expression. Unlike the regular expression fixed pattern matching, in the rule-based matching, you can define a specific token match, a phrase match, or the entity match. Earlier, we have also learned about parts of speech. So you can also specify what type of the parts of speech you want to match. So the rule-based matching is much more powerful than the regular expression matching. There are three kind of matching here: a token matcher, phrase matcher, and the entity rule matcher. So the text data which we are gonna deal with, we are gonna take it from here. That one is this one. It's Alice Wonderland. Perhaps it's the book name is there. Alright, so Alice Adventure in the Wonderland. This book we are gonna, use for our parsing purpose. This book have a total 12 chapter. So anyway, you can take here, any piece of the text data to find out a particular token match, or you can say a particular parts of speech matching or the entity matching. Other than that, you can also do the phrase matching. So in the first part of the rule-based matching in Spacy, we are going to take token matching. So in the token matcher, you can use like, the lower case of the matching, the length of the word length matching, lemma matching, the shape matching, and other flag matching like is punctuation, is digit, like, the URL matching, or you can say the fixed text data matching and the parts of speech matching. All those you can do with the token matching. All right. So here you have the Spacy installed. So recently I just installed Spacy 3.3. It comes with Spacy 2.2 as of now with Google Colab. So it uninstalled that and it installed latest version of the Spacy, which is Spacy 3.3. All right. Thereafter you can just import this Spacy and test which version of Spacy we are using. So it says that we are using Spacy 3.3. Alright, so let's go ahead and get started with the Spacy token matcher. So first of all, you need to import here a matcher. So that matcher we can get from the Spacy dot matcher. So from Spacy dot matcher import matcher, thereafter from Spacy dot tokens import span. Alright, so this span will help us to find out a particular piece of the matched word in the sentence, and the matcher will help you to match the token in the Spacy. So as usual, we need to here make a language model, English language model. NLP is equal to Spacy dot load. We are gonna load here pre-trained English model. So en core web underscore sm, which is a small model, English language model, pre-trained model available at the Spacy. Then we are gonna create an instance of the matcher object. So that's the matcher here, and I say here NLP dot vocab. All right, so with this we created here a matcher object. Once matcher object is created, now we need to find out what we want to match. So basically we want to create here a pattern first. All right, so let's create a pattern, but before that let me show you rule based matching Spacy. All right, so in this I'll show you what are the labels which you can match. So the tokens actually, so these are the tokens which you can use to match, like here auth token. So this auth token can be used to match an exact word, or you can say the exact text or the character whatever you define there. Then again here the text data, you can also use this text to match the exact word, a normalized form of the text data, lower form of the text data. With this you can match the length of the word, like let's say you want to match the 5 character word, so you can define with this. You can also match whether a particular character is alpha or ASCII or digit. With this you can match whether a particular word is lowercase, uppercase, or a title case, punctuation, space, stop word, whether a word starts with the sentence, right? So this says that the token starts with the sentence. This says that the token is made of the number, URL, or email. And this says that the token has the space here, the trailing space actually, parts of speech, tagging, morph, dependency, lemma, and shape. All these can be used to match. You can also get the annotation specifications from here. All right, all kind of the annotation specification, like here English language specification, universal parts of speech. All these you can use to match there with the token matching. All right, there are so much to learn here. The dependency parsing, English language or universal, you can use from here to find out like whether the auxiliary words you want to find, adverb or adjective or whatever you want to find, you can find out with the matcher. So let's go ahead and just get some knowledge of this text data where we want to find out something. So let's suppose that we want to find out this, Alice, and after this Alice we want to say that where this Alice is used as the noun and thereafter it is not followed by a verb. All right, so basically what I want to say here, find Alice and not verb. All right, so find Alice and any parts of speech but not the verb. So we need to make the pattern here. So the pattern is like here. Let's say first make the pattern with verb actually, then you will understand. So the two things we are going to find out here. First we are going to find out Alice with verb and then Alice with not verb. So the pattern verb is equal to, I'm going to say here, a dictionary. So in the dictionary I need to first define, I want to find the Alice. So since Alice could be used in lowercase and uppercase, so I'm just gonna convert, although the Alice, if Alice is used as the noun, then it will be always used as the title case, but still just to be safe, I'm just gonna put here match a lower case of a word. So it doesn't matter in what case this word is used, in uppercase or the lowercase, it will always try to match the lowercase of this word to the word which I'm gonna define here. So I say the lowercase of the word match with Alice, and thereafter I say match here the parts of speech. So basically it is saying that the lowercase of the Alice where it is used as the parts of speech noun. Alright, so find out in this text data all the tokens where this Alice is used as the parts of speech noun. That's mean where Alice is used as the noun. Thereafter the next token which I'm saying, find out the parts of speech where it is used. I mean to say that find any parts of speech where it is used as the verb. Alright, so I say here it is used as the verb. Alright, so this one is the pattern verb. We just created here a pattern. Let's go ahead and match this, add this pattern verb in the matcher. So matcher dot add, and in this I'm gonna say I just need to give here some name. So that's the name matching, and then I need to provide the pattern. So always provide this pattern in the form of list. So I say here the pattern verb which I created earlier. So this pattern verb now will be added to the matcher, which is the object of the matcher from the Spacy. Let's go ahead now read this text data. So I need to just get this URL from here. Then I say here, I need to read this with f is equal to open. I need to give the address of this URL from where I want to read this text data. Then I say here text is equal to f dot read. All right. Thereafter I say here f dot close. Basically I need to now close this file. All right, it says that there is no such file or the text data. Let me just hold on. All right, so since this is URL, so we need to use here a request library actually. All right, so we are gonna do here import requests. So with this request now we are gonna read this. So there I say here response is equal to requests dot get, and in that get I'm just gonna pass this URL, and of course I don't need this. Once I get that, then I say here the text data is equal to response dot text. So that's how I get all the text data. You can simply print that text data here, this whole text data. All right, although this is very huge text data. So this is whole text data. Let's go ahead and create the NLP object now. Sorry, we have already created the NLP object, but now you want to create here a doc object from the NLP. So doc is equal to the NLP text. So the tokenization is done on the whole text data. That is pretty much huge text data. So it might take some time to create NLP object there. Once that object is created, now you can say the matches is equal to the matcher which we created earlier, and in that we need to pass this doc object. So it will find all the matches which we defined there, and now we need to find out those match IDs and the span values. So match ID start and end in matches. Let's go ahead and just print this. So I say here string ID is equal to NLP dot vocab dot strings. Then I say here the match ID which I defined here. I'm just gonna get the string ID which is actually the matched one. Then I get here span is equal to doc start to end. So basically this one is whenever a token is matched based on this pattern, that will be giving us the start location and the end location. So from the doc object, we can get the matched string inside the text data. And then we are going to simply print here. I'm going to print here this match ID. Then I'm going to print here string ID. Then I'm going to print here start, end, and thereafter I'm going to match here span.text. I'm going to just print there span.text and just run this. So once I run this, we have not got anything. Seems like this is not working maybe. So one reason could be there, like it might be no place where Alice is used as the noun and the parts of speech as the verb, followed by the parts of speech as the verb. So basically I'm just gonna, put that verb here and I'm just gonna match here first Alice as the noun only, and then I'm gonna create here this matcher. So, but again, I need to get here a new matcher, perhaps from there, and just run this and then see what happens here now. All right, just hold on a second. Again, it is saying that, okay, no match. Seems like something is creating a problem when we are reading a file from the online data. So I'm just gonna copy this piece of text data and I'm going to define that here text is equal to this one here. All right, just a second. Perfect. So now this text data comes there and a new doc object will be created based on this text data only. And then we are gonna do the print. All right, again the print is not happening. Now if I remove this parts of speech as the noun as well, then see what happens. I'm gonna create here a new matcher. Well, now it says that this Alice has matched here. So basically it is saying that at these places Alice was not used as the noun, which I was looking to find out Alice used as the noun. Let's go ahead and see the text data where Alice is used, and thereafter a parts of speech is also a parts of speech verb is used. So let's go ahead and create a new matcher from here and match it with the pattern. All right, so just run this. Again it says that it did not found any of these Alice where this was used as the verb there. All right, so now what would you do here? There are the ways to find out, and there are ways to test what is the parts of speech of this Alice is here. So basically we need to again use our parts of speech lecture, the knowledge which we had gone through earlier. There you need to do like for token in doc. So we are iterating with the token. Then you need to print here token.text. Thereafter you need to print here the token dot parts of speech here. All right, just go ahead and run this and then see how this is used. All right, so with this we will be getting the parts of speech for each word which is used there earlier. All right, let's go ahead and see here at the start what is the parts of speech of the Alice. So it says that the Alice is used as the proper noun. All right, maybe that is why that Alice was not matching, which we were trying to match there. So we need to get from here this proper noun. All right, and we need to say here that parts of speech of Alice is proper noun. All right, like this. And thereafter, after the proper noun, we see that here the auxiliary words was used, not the verb is used there. Verb is used somewhere here. So after that Alice, the verb is not used. Maybe that's why we were not getting the matched word. Just to test that, let's go ahead and see after this Alice where it is used as the proper noun, and the parts of speech I want to match here the auxiliary verb here. All right, just go ahead and run this one matcher from there and do this pattern verb and this text data, and thereafter we are just gonna run this, and then we found out here Alice watch and the Alice head. These are the two token matched based on the pattern which we defined. So basically what now we can do, we can disable this text data since we have got the the ways to find out how this is gonna work. So I just disable this text data, and then I'm reading the text data from this txt file. Since this one is commented out, so it won't be going inside this NLP object, and you just run this one from here. It will take a while to get the tokens of the text data. Now here we have got, so these are the tokens in this whole text file where we found Alice was used with the auxiliary verb was, had, was, would, could, remained, did. All these were used where with this rule based matching we found out where this Alice was used actually. All right, now the other way to say here, if we want to match the Alice where no auxiliary verb was there, so how would you do that? There I say only the pattern. Let's say I say here just a pattern, the parts of speech. Now I need to define their parts of speech, not the auxiliary verb here. So there I say parts of speech, then I need to say here, I need to just get this one first, parts of speech not in auxiliary verb. So basically it's going to find out here Alice used as the proper noun and followed by a parts of speech which is not the auxiliary verb, and this pattern I need to put here, and then I need to create a new matcher from there, run this pattern and then whole request. Then we are going to provide here the matches. Let's see if Alice is used other than these tokens. All right, now you see here Alice is used so many times where the token is not followed by auxiliary verb here, like the Alice think, Alice started, after, had, to. So in this sentence, actually this had, do you remember the earlier had was used as the auxiliary verb, but in this particular sentence this had is not used as the auxiliary verb here. So that's how you can use the pattern matching, a rule based pattern matching in the Spacy. I know this lecture have been quite long, maybe like 20-25 minutes, but definitely it was the worth of watching this lecture. Thank you so much for watching this lecture. I'll see you next one. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In the last lecture, I had showed you how you can use a Spacy token matcher to find out some particular predefined pattern. In the text data, which we used, that one is this one. All right, so actually it was this one, Alice Adventures in Wonderland. That text data we used there to find out some particular pattern. The pattern which we find out, like Alice followed by auxiliary verb, and again Alice which is used as the proper noun and followed by not an auxiliary verb. So this we used. Now we are going to see here a few more examples. So based on some pattern, every time you start a new pattern, you have to get a new matcher. So we need to get here a new matcher object. Matcher is equal to the matcher. Then I say here NLP dot vocab. Thereafter I say here pattern is equal to POS, parts of speech, where we have adjective. All right, then we have here a POS, that's the parts of speech, and noun. So basically what I want to do here, I want to find out the pattern where the adjective and the noun is coming to each other. So the adjective and then followed by a noun. Then I say here matcher dot add, and in this I'm saying here adjective followed by a noun. All right, so I say here adjective followed by noun. This is just a name, nothing more than that. And then I need to pass here this pattern in the form of list there. So that's how we have added a new pattern in the matcher. Then you can get the matches is equal to matcher, and inside that you need to pass the doc object. So the doc object we created earlier for this text data, Alice Adventure in Wonderland. So that's how we got this. Matches is equal to the matcher doc object. Thereafter I need to just get this one so that we can print it here. All right, so this one is doing like match ID, start and the end is in the matches. So the matches actually produces a tuple which have a 3 value, match ID, start and the end value. Then we are getting here a string ID from the NLP vocabulary strings, so the match ID. So whenever this match is matching, it is producing a match ID. Thereafter we can also get the span. So the span is a particular part of the text data which is matching this pattern. Thereafter it is printing that matched pattern. Just run this and then see what happens. So it has produced here so many, the matches here. All these matches are here. These matches starts with the adjective. Thereafter there is the noun. So these words are used as the adjective and then the noun. All right, these are the adjective and then noun. That's how it is used there. All right, perfect. So here I'm just gonna use here a break statement to just print only one match here. All right, there other parts. So the parts were used as the noun, and here this one was used as the adjective. All right, perfect. Now let's go ahead and see here other pattern as well. So as I told you that whenever you start making a new pattern, you have to make a new matcher. So there I'm gonna create here again a new matcher. Thereafter I'm gonna create here a new pattern. So this time the pattern which I'm looking to make here, I want to get here a lemma. All right, a lemma which is a begin, actually a lemma begin. The lemma is like in the last to last lecture perhaps we had seen lemmatization. So the lemmatization produces a word into its root form. So we are trying to match a root form of any word which we say as the lemma. So we are saying here a dictionary in which I say a lemma, that's when any word which have a root word as a begin. So the begin root word is like begin, began, begins, a beginning to. All these have a root word as the begin. Thereafter I want to match the another pattern. All right, this should be a dictionary. So in this pattern I want to match here a parts of speech POS, which is actually the adjective ADP. All right, that's not the adjective, but that one is the adposition. So that's the ADP. All right, that's the adposition. So with that we created a pattern. Once we created a pattern, now we need to add that pattern here. So the name of pattern I'm giving to this as the lemma and ADP. Once you get the name of the pattern, thereafter you need to just create this matches is equal to the matcher and doc. Just run this. Once you run this, and then you can print it here, you will be getting here begin with. All right, although you can print it here like the index, then I just want to here enumerate this one. I say here when index is greater than 10, then do this break. That's mean it is gonna, hold on, this should be if index is greater than 10, then break it. It is saying that not enough value to unpack. Okay, no issue at all. So what I'm going to do here, I'm actually going to do index is equal to 0. Thereafter inside this, I'm going to just do here index is equal to index plus 1 and just run this. So at least 10 print we will be getting here. So we were looking for lemma, which is begin. So you see there the begin lemma is of course it's a begin, but here you see the begin. Begin lemma is begin, that's the root form of this is begin, and then the root form of beginning is also this begin. Thereafter we had here the adposition where begin with, begin by, begin with, all these are coming. So this rule based matching could be a very helpful to you to match a particular set of word in your text data. You can also use other the tokens to match like alpha or punctuation or space and stop words. All those you can also use. So once again we are gonna create here a new matcher. All right, and basically we will be using here a text data where Alice is there. So I say a text data. Do you remember the text data is the exact text data? So when I say text, then it will be matching exact word which I have written here. The last time when I tried to match the Alice, I used there a lower form of the token. There I used a lower and then parts of speech as the proper noun. But here I'm saying match Alice. It doesn't matter what is the parts of speech. All right. So match Alice. Thereafter I want to say here if there is a punctuation is used. All right. After that punctuation, I'm saying here optional. OP means there is an optional token. In the optional token, I want to say that if there is Alice and punctuation is used, thereafter there is optional token where any kind of token is used. This star says that any token is used after a punctuation. All right, rest of other things would be same as it is. We need to just do this one, and thereafter I need to get this whole thing to just get the print here. All right, so now it says that now you see there the Alice is used there and the punctuation was used there. All right, so any punctuation was used there, like maybe the space or other punctuations was used there. That's why we are getting these matches here. All right, perfect. So this is all about in this lecture. Thanks for watching. I'll see you next lecture. Hi everyone, welcome to Spacy 3 Masterclass tutorial. In this lecture, I'm going to show you how you can use a phrase matcher of a Spacy. This is in continuation of our previous tutorials where we were looking into the Spacy's rule-based matching, and we are working on the text data Alice Adventure in the Wonderland. In that text data, we are going to match a phrase there. So why we need to use here a phrase matcher? Because phrase matcher is much faster than the token matching. Sometimes you need to match exactly a phrase. So to match that phrase, either you can do that with the token as well, although but sometimes token is slow if there is a complex phrase. So you can simply use a phrase matcher if you have a large list of matching text data, or you can say the word data. Alright, so simply once again you need to here import phrase matcher other than what we have imported earlier. So from spacy.matcher import here a phrase matcher. Earlier we imported other other objects like Spacy itself and matcher and the span. So all these we have downloaded and installed the Spacy. So you might have watched the previous videos. If you have not watched, you need to watch those videos to properly install Spacy and import all the necessary libraries here. So once you have here a phrase matcher, now you need to get the NLP object, a fresh NLP object. So there I get NLP is equal to Spacy dot load. I'm gonna load here English core language model, a small model here. Thereafter I want to create here a matcher. So the matcher which I want to create here, that you can say matcher is equal to a phrase matcher, which we just imported here, that the phrase matcher, and inside this phrase matcher I want to pass here NLP vocab, that's the NLP vocabulary, all the words vocabulary, and then attribute I'm going to define here a lower attribute. That's mean it will match the text data by its a lower form. So whenever you pass uppercase, a lowercase or a title case, it will convert those text data automatically in a lowercase. Thereafter I'm creating here a phrase list. So you simply create here a phrase list, and inside this phrase list, let's say we want to match here some the complex token. Suppose that, let me tell you, suppose that you want to find out some complex token where it is saying some chapter. Maybe let me find out if we get any complex token here. Do we have here? Suppose that you want to find out this one. Alright, this whole thing from here to here. So you can simply copy this whole thing from there to there, and then you need to pass it here. Like I didn't mean it. So if you want to define this particular form in as the token, you have to, it will be pretty much complex to define as the token there. That's why we want to define it here. Thereafter we can take some other some other the text data where we can define, like let's say I want to match this particular no, not this, maybe something else. Which one? I'm not getting here. All right, let's say I want to match get this one. So I match here this one. Okay, let's do these two match there. Now I need to create here a pattern on this match. So the pattern is equal to for text in phrase list. All right. So this text data, we need to now convert this text data into NLP object of NLP doc object. So the NLP dot make underscore doc, and inside that I need to pass here the text here. All right, pattern is equal to the NLP dot make doc text for text in a phrase list here. All right, so the matcher dot add, then I say here phrase match. Okay, this pattern I'm going to match here. So the pattern is I didn't mean it, and this one, the much with exclamation mark there. So once all these matching is done, then I get here again a doc object there from our text data which we had already loaded in our previous lecture, Alice Adventure in Wonderland. Once you get this doc object, then you pass here matches is equal to matcher and this doc object. Just run this. Thereafter, it's very much a simple for loop where I say match id start end in matches. Thereafter, I say here span is equal to doc, and inside this I say here start end. Then I'm just gonna print here start end span and text. Well, it says that we have not found anything which is matching this particular this particular phrase there. So seems like we have to actually we have to make it simple just to make sure that if it is working properly, maybe something like this. Okay, that's the phrase list. We need to get here this matcher once again. Sometimes it will take to create this doc object because it was the quite large. So it says that it has matched this one but not this one. Not sure why it did not match that one. This should have matched this one, maybe because during the tokenization it might not have got this one. So maybe you can match this one. Just a second, let me see if this can match that one. Get a new matcher and then like this. All right, once again it is matching just this one here, none other than that. All right, so we are seeing here only a this first token match because there is a special character here inside that. So you need to remove that special character. Maybe you can match this one C had expected. So basically I can put that here. Thereafter I can match this one C found her. So how many times C had expected and how many times C had found her is matched in this whole story. So need to run matcher equal to the phrase matcher, then phrase list pattern matcher dot add doc matches is equal to the matcher, and then just run this. All right, so it says that there is just one occurrence of C had expected and C found her. Suppose that I just want to say that C had and C found, how many times this happened, then I just need to run this once again. You will be seeing here a complete list of C had and C found. So here many times this, the phrase has occurred in this particular text data. All right, perfect. So that's how you can use a phrase matching. This phrase matching is much more efficient than the token matching. Otherwise, you can do everything with the token matching, whatever you can do with the phrase matching. All right, this is all about in this lecture. Thanks for watching. I'll see you next lecture. Hello everyone. Welcome to Spacy 3 Masterclass tutorial. In this lecture, we are gonna see entity matcher. So this lecture is in continuation of rule-based matching in Spacy. Previously, we have seen how you can do the token matching and the phrase matching. This is the last part of that series. In this lecture, we will be seeing how you can match the entity like organization name or geographical location or some person name or money or currency or something like that. So for that, you need to import a Spacy and then a pipeline of the Spacy, which is the entity ruler and English language model. So you just need to import this. And now we are gonna take here a predefined text data. This text data is like the first state includes included the clergy, that's the church leaders. The second state included the nobles, and the third state included the commoners. The third state paid most of the taxes while the nobility lived lives of the luxury and got all the high ranking jobs. Alright, so this one is the text data. In this text data, we are trying to find out the entity names. Alright, just run this. Thereafter, I need to make here an English language model. So NLP is equal to English. This is the blank English language model. In this ruler is equal to, you see here we have taken a blank model. Earlier we were loading a predefined, a pre-trained small model, EN core wave small, but this time we are taking a raw model, a blank model. Inside that blank model we are adding here a pipeline, which is ruler is equal to NLP dot add pipe. Inside that I'm saying entity ruler. So we added a pipeline in our language model as the entity ruler. Let's define the pattern which I want to match here. So the pattern is equal to, inside that I say here label noun pattern. Inside this we have here a church. And then we have here label org, that's the organization. Pattern alright, we have here lower the. So basically we are matching here a noun label. The pattern is the church. So the church, wherever it is used as the noun, followed by a organization. Alright, the label which is as the organization. The pattern, once again I'm trying to match here the lower form of the pattern, which is actually the there. Alright. So something is missing maybe? No. We got here this particular pattern. Okay, so the label is organization actually. The pattern here we are matching, that is the. Alright. Thereafter we are trying to match here lowercase. Alright. Inside that I want to match here a lowercase where it is used at the first, second and the third. So the lowercase of any token which is in first, second and third. Alright. Then auth, that means we are trying to match an exact word here, which is a state. Alright, perfect. So how we are matching here, we are matching a church which is used as the noun, thereafter a pattern which is the lower form as the, and again another token's lower form is in first, second or third, and then an exact text word which is a state. Alright, we just run this. Thereafter I say here ruler dot add patterns, then I say here this patterns. Just run this. So this pattern is added in our entity ruler. Thereafter you need to get the doc object. So the doc is equal to NLP and then text. So this text data is passed in this NLP object. Inside this NLP object we added a pipeline which is entity ruler. So inside this entity ruler pipeline we added a pattern. So this pattern will be executed inside this object and that is placed in this doc object. So I can now print here I can the print here for ent in doc dot ent. All right, then I say here print ent dot text, ent dot label, ent dot ent id underscore, and then again underscore. All right, that's the entity id. Just run this. So what we have got here, we got the first state, which is organization. All right, that's when this is some organization, and then the church is used as the noun. Thereafter, the second state, the third state, and the third state, which is used as the organization. So that's what we got from here. Now, if you see there, we got noun, a pattern matched, which is noun used as the church. So that's where we got here. We also got here organization. Label is organization. That means this overall label is organization, which has a starting pattern as the lower form of this text data as the, and then again next token which falls inside first, second, and third, and then exact text match, which is the state. So that's how you can use entity ruler or entity matcher to find out a particular entity in the text data. Whenever you have a large text data and you want to do some kind of the matching, or you want to get some kind of the text data or a substring from that data, or you are doing like the labeling of your text data, maybe you can use a rule-based Spacy matcher to do the labeling of your text data. All right, this is all about in this lecture. Thanks for watching. I'll see you next lecture. Hello. Hi everyone. Welcome to Spacy Masterclass tutorial. In this lecture, we are gonna see how you can do named entity recognition. A named entity recognition in Spacy is very useful when you have a large data set and you want to find out some entities inside the text data. You can use either a pre-trained NER model from Spacy, or you can train your own model in the Spacy. There are use cases of the NER such as resume parsing, or you can say a CV parsing, in which you want to know the skills of a person or a name or a previous experience or a company name of a person. Other than that, it is very useful in the pharma where you want to get the medicine name. Other than that, in the some text data where you want to identify the product's name. So there are many uses of NER in a practical NLP. So basically, the entity is a real life object which has a proper identification and can be denoted with the proper name, such as a place or any place name like New Delhi, New York, London, a person name like Elon Musk, Donald Trump, or Barack Obama, organizations like any organization like NASA, Tesla, Apple, Facebook. The time is like today, yesterday, or some date, and some kind of the object there, or you can say the product like the apple, orange, and these, and some geographic entity like country name. So all these can be detected by using NER in Spacy. And the named entity recognition means identifying the named entity from the text data. So it looks like something like this, where you have a large text data and you can identify these tokens if these tokens matches with some predefined entity types. Like this Chinese matches with the NORP. So the NORP says that this one is nationalities or religious or political group. That's when this one is nationalities, which is Chinese nationalities. Market has a 3. So 3 is cardinal. So the cardinal you can see here. So the cardinal is numerals that do not fall under the another type. That's when this one is numeral. Alibaba is GPE. So GPE is country, city and state. Although this is wrong here. Alibaba should be organization, which is company and agencies, because this NER is not 100% accurate. It's like 85% accurate. 85% accurate. If we are talking about a general purpose NER, it's 85, and transformer based NER in Spacy is accurate like 90% accurate. Baidu is organization, that is correct. Tencent is a person, so this one is also wrong here. This one is also organization. All right, the AI, it is saying that AI is GPE. AI is not a GPE. This is a technology. US is GPE. Okay. Now you see there here AI is GPE and here it is a person. So yes, these are wrong here. As I told you that it is not 100% accurate. And here CAGR is a person. This is not, definitely not a person. A percent, that's correct. This one is the date. This is also correct. So most of the things are correct here, like Google, IBM and the Microsoft. So moreover, we can say that it is accurate like 80 to 85% in a real world data set. So these are the type of NER entities which you can identify using Spacy NER recognition, like a person and nationalities, some some building, airport, highway, if it is FAC, organization, GPE, LOC. LOC is non-GPE location like mountain range, bodies of water, etc. Some product like objects, vehicles, food, etc. Not services. Event like named hurricanes, battles, wars, sports events, etc. Work of art there, law, language, date, time, percent, money, quantity, ordinal and cardinal. So the ordinal is like first, second, third, etc. The cardinal is like number 1, 2, 3, 4, 5, something like that. So as I told you that the basic NER recognizer, is as much accurate like 85%. But if you use a transformer, that could be as accurate as 90%. So whenever you are looking for accurate NER recognizer, you should be using their transformer based recognizer. But the transformer based recognizer is very slow as compared to general purpose NER recognizer in Spacy. You can install a Spacy. As usual, we have been installing Spacy with these commands here. I have installed here a small model and the large model of the Spacy, which is already a pre-trained model, and it has a Spacy 3.3 installed there. And thereafter we will be also doing NER recognition from a text data, from a news site text data. So for that we will be needing here a beautiful soup 4 and LXML. All right, perfect. So this is all about in this lecture. In the next lecture, I'll show you how you can download these data from the news site and how you can do the NER. Thanks for watching. I'll see you in next lecture. Welcome to part 2 of named entity recognition. In last lecture, we have seen the introduction of NER and we installed necessary libraries. In this lecture, we are gonna start doing some practical work. As usual, we need to import here a Spacy. If you want to know the Spacy version, you can simply say that Spacy version. It will be Spacy 3.3 currently. That's the latest one by the time we are making this lecture. And let's go ahead and take the raw text data. So the text data which I'm gonna take here, text is equal to, I'm just going to take the text data, the random text data from here. All right, I just need to copy that text data from there. All right, so on this text data, I'm gonna run a pre-trained NER model which is available in Spacy. So it is a very simple model. I need to get here English language model in NLP. So spacy.load. Inside this I have here EN core web LG. So the LG is large model. SME is not as much as accurate like LG. That's why I'm gonna use here a large model. So Spacy large model. Thereafter I need to get here a doc object. So doc object is like NLP and then text. All right, now I have got this doc object from the NLP. Now I can do like for ent in doc dot ents, that's mean get all the entities in the doc object. Thereafter I need to just print it here like ent dot text and then ent dot label. All right, so here we have a label ent.text data that will be printing the text data and other related label here. So as I told you in the previous lecture that it will be identifying all these, the type of the NER available in pre-trained Spacy model. So it has identified in this text data Tesla as the organization, definitely it is correct. Twitter as organization, San Francisco as GPE, Twitter as the product. So at this particular place Twitter is mentioned as the product and at this place it was mentioned as organization. I believe that it is correct in both cases here. Because you see here at Twitter's headquarters, so definitely it is mentioned as the organization. But here Twitter shares are around, that's mean it is mentioning here as a product Twitter. A 27%, which is here a percent, Mr. Musk as a person, and this one is as money. Now you see there, this one is mentioned as money. This week as the date, US again GPE, district code as the organization. Yes, definitely this is a place, and northern district again this one is LOC. So LOC is also a location, but that is the not GPE location, a non-GPE location. All right, California is there and William Harris Naki is there. So it has identified here the mostly correct NER out of these text data. Now you can use this whole text data, this whole news as the text data to find out a complete NER inside this news. So by seeing this NER, you can also get overall overall meaning of this particular news article. Like this says that something is being talked about, like Tesla Twitter in San Francisco, some 20% maybe the stack or like that, some about the money in the US. So with this you can also identify overall summary of a news article, what is being discussed inside this news article. All right, let's go ahead, and if you want to know the description of these NER tokens, how you can do that, it's pretty much simple. You can simply do that like Spacy dot explain. Let's say you are not sure what is this org, you can simply say that Spacy dot explain org. It says that companies, agencies and institution. Similarly, if you are not sure with LOC, you can find out here LOC as well, non-GPE location like mountain range, bodies of water, etc. All right, perfect. Now let's go ahead and do NER classification for this news article. So for that I need to import here a few libraries. So first of all I need to import from BS4. I installed that beautiful soup 4. From BS4 I need to import here a beautiful soap. All right, beautiful soup. Thereafter import requests. So with this requests I'll be downloading the text data from the news article and then import RE. I may not need that one. Basically I need here from Spacy import Displacy. All right, I'm gonna import here Displacy, that I'll be displaying the text data, something like we had seen earlier, something like that. So this one is displayed by using a Displacy. All right, perfect. Let's go ahead and get the URL which we are going to use to read the article. So here I have this URL. All right, I say here the HTML content. I get HTML content with the beautiful soup, with the request, and then I can parse this HTML request from the beautiful soup. So I say here the requests dot get, and I'm gonna get from the URL which I defined earlier. Thereafter I'm gonna get the text data from there. So now if you say there the HTML content, you will be getting here the HTML content of this particular text data. So basically that one is something like this. All right, this HTML content there we have got. All right, perfect. So once you got the HTML content, thereafter we need to parse this HTML content. That you can do with the beautiful soup here. You can simply say here a beautiful soup. Inside that you can pass your HTML content, and you can also pass here the parser. So I'm gonna use here parser as LXML. With this parser we'll be getting this soup. All right, a soup object. Inside this soup object you can get the body is equal to soup dot body dot text data there. Thereafter you simply do here a body. Inside this body you will be getting this whole body text data there. All right, perfect. Now once you have got this text data, that's the body text data, thereafter you can simply do something like this, and then you can do this print there. So basically I need to get here the doc object. The doc is equal to the NLP and there this body text data, and then I need to simply print it here. All right, after printing this I have got here all these whole text data. There's so much a text data here. All right, so many things. So if you do some more pre-processing, you can remove these these things there, and then finally you can get a pure text data out of these printed text data there. Now if you see there, the mostly all of these are correctly identified here, like Ukraine, Indian, Colombia, everything. So basically it has taken this whole text data from here, all these storage data and the footnote and the head note, everything, and out of those it is trying to print all these things here. All right, so if you want to do just on the text data which is in your interest, you can using a beautiful soup to get these text data, although that is not the part of this lecture to tell you how you need to do the beautiful soup. Maybe some other time I'll be taking some lectures on the beautiful soup where you can read a particular news article, like only this much of the text data from this particular article. All right, perfect. So that's how you can get that of a whole news article. And other than that, if you want to see this on Spacey, you can use the Spacey as well here. So you need to just do here Spacey dot render. Inside this you need to pass the text data, that's mean the doc object which we created earlier, and inside the style I need to say here I need to parse here entity. And since I'm using here a Jupyter notebook, I have to say here Jupyter is equal to true. Just run this, you will be getting like we got the earlier, something like this. Right, from the starting, if you see this, let me just show you it from the starting. So from the starting you see the BBC homepage. This says that this is organization. This is definitely not the correct here. And Elon Musk as the person here, again here it is a person. Twitter as the organization, Twitter as organization, this week as the date. So now you see all these things are correctly identified here with the Spacey. You can display this in a very beautiful very beautiful chart, or you can say the inline text there. These are the highlighted text. This shows really a very beautiful text data here. So this is all about in this lecture. Thanks for watching. I'll see you in next lecture. Hi everyone. Welcome to Spacy 3 Masterclass tutorial. In this lecture, we are going to study about the word to vector. And we will be also seeing how you can do the sentence similarity in a Spacy. Before we get started with this lecture, you need to understand what is the word to vector. Just for an example, you see these three representation of the vectors. Since we are dealing with the text data, so machine learning algorithms cannot handle text data directly. There has to be some way to convert this text data into a numerical form. There are other ways you might know, like TF-IDF, a bag of words. So these techniques converts a text data into a numerical data. And the same way, there is a way known as word to vector, which converts a text data into a numerical vectors or a numerical data. Then you can apply machine learning on that numerical vector or numerical data. Suppose that you have given a text data something like that: man, women, king and queen. So how would you represent these four words in a vector? You cannot assign random vectors to all these four words, because there has to be some logic and some sense when you give a vector to these four words. Because traditionally, if you see, man and women is quite related to each other, and similarly king and man, these are related to each other, and then again queen and women is also related to each other. So whenever you give a vector to these four words, there has to be a similarity between the vectors. Whenever you assign a vector to this word, this should be near to this vector, and this vector should be near to this vector and this vector. So this one is represented in a 3 dimension. Although when you do word to vector, the dimension is quite high. So when you represent the vectors in these dimensions, that is known as the projected vectors. All right, so the projection, or you can say the projected dimension. Here you have a 3 projected dimension, that's mean a 3D vector here. But in general, we get like 100, 200 or 300 dimension vector. That's mean a word is projected into a 300 dimension. When the dimension is large, then in that case you have a high space, a large space to represent a vector accurately. That's mean that there you can project a large number of dictionary there. Similarly, if you have given these 4 words, you know that this walked and this swimming are not related to each other. So this has to be, at a distance. And similarly, walking and walk, these are correlated to each other. So these vectors can be nearer to each other. And similarly, now you see there Spain, Italy, Germany, these are the European countries. So mostly these countries will be coming together in the vector space. And similarly, these cities are capital of these countries. So these would be also correlated to each other at quite close places. Similarly, you have these places here, you see there, these are quite related to each other. There, Vietnam, China and Japan, the Canada and the Russia. So these are, nearby to each other. When you project a vector in a projected space, basically the vectors should be nearer to each other, and similarly their capitals also close to each other. That's how this grouping happens when you do word to vector. That's when you convert a text data into the vector. All right, so that's the concept of word to vector, why this word to vector is needed. So what is this now? Now, what is this word to vector? This word to vector is actually a technique in natural language processing where you convert text data into a numerical data. It was published by Google in 2013. This word to vector technique is also patented by Google in 2013. This word to vector algorithm uses here a neural network, a 2-layer of the neural network. It is trained on a large data set, and then finally at the output layer a vector is produced where the similar words are kept near to each other. so that when you pass a two word which is almost a similar word, you will be getting their high similarity matrix. So the similarity is calculated with the cosine similarity method. All right, you can get the detailed description of word to vector at this link here. This is quite good link. Let me just open this link. And also you can get the TensorFlow implementation of word to vector. So at this link you will be getting a very detailed illustrated word to vector description here. He has explained this in a very detailed. So the detailed explanation of word to vector is beyond the scope of this lecture. So I'm skipping this detailed description of word to vector. Although if you want to go in deeper, you can go through with this lecture. Similarly, word to vector implementation of the TensorFlow, you can also go through with this link. So this says that word to vector is not a single algorithm. This is a combination of the algorithm, a family of the model architecture, which produces finally a word, or you can say the vector there, word to vectors there. Basically, the two methods are used to produce the word to vector: a continuous bag of words model and continuous skip gram model. It is your choice whether you want to use a bag of words model or a skip gram model there. But in in this Spacy, you don't need to go through with all these details. Spacy have given, Spacy have given you a pre-trained model which you can use to get the vector there. All right, let's go ahead and get started with the Spacy. So as usual, you need to install a Spacy, something like that. If you don't have a setup tools, install setup tools, Spacy, and a small model and the large model. A small model don't give vector word to vector in Spacy, so you will not get any vector representation in a small model. You have to get the large model to get the vector. Medium model also have a vector, but still you should get this large model, because this large model have almost 700,000 unique vectors. So it's actually 685k unique vectors it has, these models. So basically, what I mean to say here, there are almost 700,000 unique tokens are there, which this Spacy large model have already pre-trained inside. All right, let's go ahead and import Spacy. So here I'm gonna import Spacy. NLP is equal to spacy.load en core large model. En core web LG. I need to give this inside the bracket there. All right, a language object is created here. Thereafter, let's go ahead and get the token. That's mean the doc object. So I say here, this should be actually the doc. Doc is equal to NLP, and inside that I'm gonna say here dog, cat, and then I say here bird and some random words like something like this. All right, so these are the token. Now you see these are the most common token in English language, but you may not get this in a dictionary, English dictionary. So it's very less probable that Spacy might not have this vector inside its pre-trained model. Let's go ahead and check this. You can check this for token in doc. Thereafter you can say here print token dot text and then token dot has vector. So with this flag you can say that whether a particular token have a vector or not. Thereafter you can say the token dot is out of vector, that's the OVV. All right, sorry, out of vector, that's OOV. That's mean this will print if it is out of the vector. Any of these token is out of vector. Let's run this. So it says that the doc have a vector, this one have vector, this one have vector, but this one do not have a vector. That means this is out of vector. That means Spacy do not have a vector for this representation. Basically what it will do here, it will give you a zero vector, which will be directed into, which will be actually projected into a 300 dimension. So there would be a sequence of 300 zeros for this particular word. All right, let's go ahead and write some code to get the similarity between two sentence or two word there, or you can say the two document here. All right, so I say here text one, the text one, I'm gonna say like I like salty fries and hamburgers. This is one text. Then in text 2 I'm saying here fast food testers fast food tastes very good. So these are the two text data. Now with this text data, you know that these are quite related to each other, because salty fries and hamburgers are fast food, and we are also discussing here a fast food in second text data as well. So just run this. Thereafter I need to get here the two doc objects. So the doc one says that here NLP text one, thereafter doc 2 is equal to NLP text 2. All right, then I say here print doc 1. I'm just gonna create here I'm just gonna print here both doc here, doc 1 and the doc 2. Thereafter I'm gonna say doc 1 is doc 1 dot similarity with the doc 1. That's mean it will be printing here the similarity between doc 1 and the doc 2. This one is known as a cosine similarity between two vectors. All right, so just run this and then see what it is gonna print. It says that these two are quite related to each other. So of course doc 1 and doc 1 have 100% relation to each other, but if you put there the doc 2, you will get it is related like 72%. Let's go ahead and test it with some more text data there. So something like that there. I'm gonna say here river bank, and then I'm gonna say here bank account here. So the problem with a general purpose word to vector, that it does not take the context of the word. So now you see there the bank here, this bank means something related to a place that is beside this river flow, and at this place this bank word means this is a financial institution here. All right, let's go ahead and just print this. You will be seeing here a very high accuracy, although very high similarity metrics between these two sentences, although you know that these are not much related to each other. All right, so that's the problem with the general purpose word to vector representation. So one way to get the more accurate representation, that is use of the transformers. The transformers, if you use transformers, you will be getting a more accurate representation of the vectors. In coming lectures, we will be also covering the transformers, how you can use the transformers to get the sentence similarity. Let's go ahead and take this just river and then this bank and then see how similar it is. Now again, now you see there this river and bank. In this context, it has taken this river as the river and this bank as a financial institution. That's why the similarity is not that much. All right, although there is some similarity like river bank and the bank might be coming to each other. That's why it is a 42%. So with these two, you can finally get the sense that this general purpose word to vector does not take the sense of the context of this word, right? Because although it is a same word, but the context is different here and in this sentence there. All right. So this is all about in this lecture. Thanks for watching. I'll see you next lecture.